The temperature, you have to maintain it as minus 217. Yeah, I know, it's Canada. 200 is not a big deal. We can handle it, but it's very costly. You have to have helium gas and nitrogen gas all the time. It's very costly and expensive. So don't panic when they charge you for $2,000 per second. Okay, and another thing for quantum computing that you need to consider, look, yes, in quantum algorithm we say we apply this gate, we apply that gate, but in practice we're dealing with fragile particles. We're dealing with a little defect in nanometer size in a diamond, which is so sensitive to environment, to any change in the environment. So definitely we have errors. And those gates that we wish to have quantum supremacy, quantum advantage, in practice, once we want to implement them, we may implement something that is similar, not 100%, but we have quite advancement here. For example, superconductor, we can achieve 99%, or in these center. But with neutral atoms, because they're interacting so weakly with each other, it's very hard to get together 2-qubit gates, and the fidelity is normally low. We should keep in mind that in practice, when we are building these quantum devices, the quality of initial state and the quality of each individual gate matter. We should also be careful about the speed. These systems are intend to lose coherence so quickly. So the coherence time is in the range of microsecond, millisecond, a second. It's short. We need to know that we have some time to do our computation before losing all the quantum properties. Within that time, we have to implement the number of gates that we need for the quantum algorithm, but there's a limitation there. Remember the quantum phase algorithm? If we wanted to achieve higher accuracy, we needed to apply more and more gates, but that's not possible in practice because you're losing time. There's a cutoff that you have to put. For some systems like ions, you can do very fast, 10 to the 13 gates within the time you have, but for others it's 10 to the 4, something like that. So just keep in mind, I don't want to bother you with the numbers. I just want to, when you go home, think about it like these quantum algorithms are designed in the ideal case, but in practice, we do have to deal with coherence time and the limitation that we have because of that specific quantum system that we picked. Okay. Another thing that we need for building quantum computer is the scaling. Your laptop, how much bytes you have in your laptop? 500 gigabyte, 200 gigabyte? So it's not going to be 1 byte, 2 byte, 3 bytes, 50 bytes. So the same with the quantum computer. At some point, if you want to factor the numbers that Amir gave you, you have to scale up. And these platforms that I picked as an example, they do have the potential to scale up, but they're extremely challenging. For example, for superconductors, we're fabricating those devices, right? We are fabricating the LC circuits, or in quantum dot, for instance. Once you want to scale up to the 3D or 2D and then have like 1,000 of them sitting in an arrangement, it's a challenge, both not only in the fabrication and engineering, but also once you fabricate it, then you may compromise the quality of individual qubits or the quality of each of those gates that you apply. Maybe you want to do computation qubits 1 and 5, but because you're turning on your microwave, qubit 2 and 3 in between are also talking with each other. These are the leakages that you don't want to have. Okay, but despite all of this challenge, quantum race is happening. And we're so excited to be living in this time. If you look at the ecosystem, it's growing fast. Especially over the past 2 years, you can see numerous startup companies showing up, like Xanadu. Most of these big companies like Google, IBM, and Intel, and Rigetti, they're taking the universal approach. When I say universal, it's the gate-based model, and they want to build a computer that can do any computation. But some companies are task-oriented, like D-Wave that Amir talked about. They use technique like quantum annealing, which is different, and I haven't talked about it here. And Xanadu also is doing quantum sampling, and it is, again, one specific task that a quantum computer can do better than a classical one. And these companies, because when you put money anywhere, then golden trees are growing up. Because of the existence of industry in this area of research, now we have new softwares that are developed mainly by these companies, like Strawberry and Penny Lane by Xanadu, that was published very recently, and Forest, for example, by Raggedy, and Q Quantum Information Ski by IBM, and the other Q Sharp by Microsoft. So the ecosystem is growing, and the companies, despite all of the challenges, they are taking this seriously. We should ask this question seriously too. Is quantum computer ready for real applications or not? I know, it's up to you. Yes and no. I'm giving you all the facts. For some quantum algorithm, as you saw, like for example, factoring, after some point, I don't know, was it 80 digits for factoring? After some point, you see that the quantum is doing way better than the classical one. But before that point, you don't get quantum advantage, right? So where that point is exactly depends on the problem. Is it factoring problem? Is it phase estimation problem? And then you need to ask, do I need 50 qubit, 100 qubit, or 1,000 qubits to see the quantum advantage? You should also ask yourself, is it just the scaling that matter to get the quantum advantage? Not really. The qubit quality matter. Yes, people announced that we built 50 qubit size, 2,000 size. But somebody has to go and see whether we do have the qubit quality for that specific quantum algorithm or not. The gate quality, the connectivity, the leakage, everything. I'm not saying that this is not, those devices are not capable of doing that. I'm just saying that we have to consider all of these facts. How about the errors? Errors, we cannot avoid errors. We always have errors in initialization, control, and gate detection. In all these steps, we have errors. And normally for these gate-based computation, people, at the top of that quantum algorithm, people run error correcting algorithm. And you should also test whether their device is doing fault-tolerant, the so-called fault-tolerant quantum computation or not, which means that it is robust to errors up to this limit. Okay. And at the end, whether these quantum computer, for sure, it will revolutionize all industries. It's not just encryption, it's not just in cryptography. These days, we're doing computation anywhere. Living in Xanadu, even we were talking with companies who are making animal products. All companies are doing computation. For drug discovery, material, for even getting statistics from their customers. So computation, we cannot avoid computation. And as soon as a quantum computer is built, then most of these industries are affected. So whether it's happening in 5 years, 10 years, 20 years, nobody knows. But what we can ask at this moment is that these quantum devices that are built already, they are noisy, but we might still be able to do some computation with them. And then depending on the task that it's given, then you need to ask whether these noisy quantum devices outperform the classical one or not before purchasing it for your child. Thank you. And I want to get this chance and thank anyone that I have worked with over the past decade. Don't calculate my age. And thanks.
Thank you so much, Razia. That was a magnificent presentation. It's a privilege to listen to you speak about this. We do have a question from Twitter. Yes, we do. Let's see if I can find it. How are these physics theories applied to computing? And are there any books specifically where someone could find out more information?
Well, there is a holy book in quantum information, quantum information written by Juan, but It depends from which angle you want to approach. If you want to learn about the bottom line, that how these algorithms are actually performing, then you need to look at the basic books of quantum mechanics. And it depends, again, on the system that you're choosing. If you want to learn about, because each of these branches is a whole different world. If you want to learn about quantum optical side, just learn about quantum optics. If you want to learn about superconductors, you have to know how, you have to know a little bit about electrical circuits, right? So depending on which platform you're interested in, then the sources are different. And that's from the fundamental side. But if you just want to know how the quantum algorithms are working, you don't need to know physics. So all you need is that, like, mathematically and theoretically, how a qubit is working when a gate is applied or an evolution operator is applied. But when it comes to realization of this system, where you want to actually see how these algorithms would work on this device that is made of diamond, or that device that is made of quantum dots, then there you have to know about the fundamental of that particular system, the physics of that system. And the resources, I would usually start with lectures, because lectures avoid complexity, and also some holy books like wine, as I said.
That was a fabulous answer. Thank you so much. We're also going to open up the floor if anybody has any additional questions that they would like to ask Razia. John, there's a hand over here. John's just going to bring you a microphone.
A quick question, because we're running a little bit behind.
Thank you for this. But, we were having a discussion that day about the quality of the qubit, and that scaling, like D-Wave to 2000 is like way too much, and they maybe because they're focused on specific kinds of things. How do you think is it practical to scale up to create like a universal quantum?
Fundamentally, I don't see obstacle, but practically, when you want, for example, I talked about superconductors because you mentioned E-wave. In a superconductor, you're controlling the dynamic of system by applying voltage. When you are doing fabrication, then at the surface of those nanometer size pillar, for example, you have some little dangling bonds electron. And those electrons by themselves, they are a source of voltage. So, and because the system is so delicate, the noise source might be comparable to the voltage control that you're applying, right? And when you want to scale up, especially if you want to go to the 3D, then the electrons of this layer may affect the device in this layer, and that may affect this one and that. So you are kind of entangling them all. In one side, you want each individual qubit to be an isolated island, not talking to others. But on the other side, for certain computational tasks, you want a group of qubits to talk to each other at the same time. And it's extremely challenging. I'm not an engineer to make a comment saying that it's impossible or it's possible. I'm a theorist, and fundamentally there's no obstacle there. But practically, from what I see, it's challenging. And I haven't tested D-Wave's device to make any comment on that. But I'm just guessing that just scaling up to 2,000 without compromising other quality, I don't know.
Thank you so much, Razia.
Thank you.
Thank you.